Good afternoon, everyone. My name is Siva Poornan. I am a doctoral student at the Civil Engineering Department of IIT Madras, and here we are meeting for the sixth week for the course of Matrix Method of Structure Analysis, and we are having a live interactive session to discuss regarding the course contents and doubts and discussions on the same. So, what we have been discussing in the last 5 weeks is that we were discussing first revising basic structure analysis, and then we were slowly proceeding towards displacement method of structure analysis, and then we got into using stiffness matrix. That's what we call as matrix method of structure analysis, and we did it for truss problems, and then we have moved on to beam problems, and then this week we'll be proceeding from there and discuss on more details on analyzing beam problems. Especially we'll also get back to truss problem and see some minor details which was asked last time, and then we'll also do similar discussion for a beam problem, right? So at this point I would like to ask, if you have any questions, we can discuss that first on whatever we have covered earlier, and then we can proceed on to the other details. Do you have any questions from the assignments or anything else that you have seen in the course in the previous weeks? Okay, then I would consider that you don't have any questions, and I'll get started with this week's discussion, right? Fine. So what we were discussing particularly last week was on a beam subjected to nodal forces and moments, and in turn has nodal displacements and rotations, right? And how do we connect them? Using the stiffness matrix. That's the usual method that we have been seeing for the last few weeks. So if there are some forces and moments applied to the nodal points of a beam, then we can relate them as, let's say, F1, M1 are the forces and moments at the first point A, and similarly F2 and M2 are the nodal forces and moments at the second point B. Then I can connect them using a stiffness matrix, which I can build using the typical procedure. We have discussed this also in the previous week, right? Now, something else was also covered in the last week, which unfortunately did not come up in the recording. So I'll briefly reiterate it again so that it gets covered in the recorded lecture, right? So what we had discussed was, so this problem we would be able to solve if there is a beam subjected to n forces and n moments. We would be able to calculate the n rotations and n displacements. Till this point, I hope it should be clear. If you have any doubts in that, you can ask me now. So I hope that's clear to everyone. If that is the case, then what can we do in a case where the beam is not subjected to just n forces and moments, but also to intermediate loads, right? So let's say we have a same beam structure. Let's just take a horizontal beam structure for time being, and then let's say it is subjected to some. Let's take a real example with boundary conditions. Say we have a beam like this, and it's subjected to intermediate loads. Then what do we do? In this case, we would not be able to find out. We are not directly given with n forces and n moments for us to solve it. If this was not the case, if these loads were not given, instead these loads were given, let's say there are two moments applied at these two ends, m1 and m2, then we could solve this problem. We have already seen something similar in the earlier lectures, and we would be able to do that. But if n forces are not given but intermediate loads are given, then we need to split it into two problems. That we can do through a very clever method, superposition principle. What we say is that we first split this problem into a fixed problem. So what we do is that we say that this intermediate supports are not, it will always make it as a fixed case. Why? Because a fixed beam is a kinematically determinate beam. We should be able to solve it using the force methods, right? So what I am going to say is that I'll just make this beam into a fixed beam. Instead of this roller support, let me just put a fixed support. That means on the other side also it's fixed, right? So I'm splitting into two things. But if I'm able to do this, which means that I'm going to, what does it mean by giving a fixed support at the end? It just means that I'm giving an extra moment here, extra moment such that the rotation at this point becomes 0. That's what it means, right? So I'll just erase this moment because actually we are not given with n moments. So I just put this for illustration purpose, right? So the actual loads are given in black, which are the intermediate loads. Okay, so if this is the case, then we are supplying some extra moment here. It can be in any direction. I'm just taking it as clockwise. So it is some mf1, okay, and some moment here, mf2. So these moments correspond to the moments that would make the rotation at this point 0. Okay, so if I'm adding these moments, that is equivalent to saying that I'm giving a fixed end support here. These two are equivalent. These were same sentences in different ways of saying. But only problem is that if I'm giving a moment, we should also give a negative moment so that the total system does not get affected, right? So basically what I have to do is that I'll solve this problem, and in a separate problem, so these loads I will keep as such. Whatever loads, intermediate loads are there, I will keep as such. And whichever moment I applied, or in other words I gave fixed support to this, I'll add a reverse moment at that point, right? So I would have added a moment like this here, mf1, it could be mf1 and mf1 dash here, right? This moment itself will get split into two things for the two parts of the beam, right? The notations might be different from what you would have seen in the course, but the concept is what I'm trying to stress here, right? So the total moment that I have given, I have to give the opposite of it here, so that I don't, in summary, I would not disturb the beam. Okay, similarly whatever moment I had provided there, I will give the opposite of that here. So this will be same of mf2, and this will be just the sum of these two things, right? So in this way what I'm doing is, one case I'm adding the moment so that it becomes a fixed end beam, and in another case I'm giving the reverse of it so that I don't disturb the total structure. So these two structures put together is what going to give me the actual structure, right? So this structure I know to analyze from the structure analysis, matrix method of structure analysis, which we had seen in the previous class, and this thing we know to solve using the force methods that we would have seen earlier in the course itself. So this we know, if we have a fixed beam subjected to some intermediate loads, I can solve it using conjugate beam method or any other methods that you would be familiar with, right? So therefore this is, both these problems we know to solve, which means in total we know to solve the actual problem given to us, right? So this is the way you can solve a beam subjected to intermediate loads. You split it into two problems. One problem you make it kinematically determinate and then solve using force methods that you would already studied, and the second problem is just the same beam with same boundary conditions, but the loads are only joint loads. So those things we know how to solve it from the matrix method of structure analysis, which you have seen. So therefore we would be able to solve the end rotations and end displacements for the given end moments or end forces, right? So this is a brief summary of how we would solve beam subjected to any forces. It could be intermediate loads or end forces, right? uh, so at this point I would like to mention one thing. In the previous week there was a question on, okay, we are able to solve for end rotations and end displacements, but we are not able to solve for intermediate displacements. What I mean by that is, so by solving these problems we can find out the displacements and rotations at any point in this beam, right? Using conjugate beam method you would be able to find out, right? So let me say y1 of x, you would be able to solve, right? Similarly you would be able to solve for But here in this problem we are going to use, in the second structure, I'm going to solve only for n rotations, right? So I would know what is the rotation at this point, right? I know what is the rotation at this point, right? And I know the rotation at this point, which is 0 from boundary condition itself. But how do I find the displacement and rotation at this point, any point, let's say somewhere here? How do I know? This might be of interest when you are actually doing an actual problem, right? Because your maximum deflection in a structure, what you might want to do is that you might want to check whether the deflection is exceeding a certain value. That means that you need to find out what is the maximum deflection throughout the beam where it is happening, and that point should not deflect more than a certain level, right? So for example, if you see here, the deflection here is maximum and deflection here is somewhat looking like maximum, right? And these 2 points we might have to find out the deflection. How do we do that? We only know the rotations and displacements at the nodal points, at the joints, not intermediate. So how do we do that was a question that was asked last time. So I would try to address that question in this lecture, right? So first, before going towards beam, let's just first talk about what happens in a truss and then proceed on to beams with similar concepts, right? So first we will just analyze the truss and see how do we find out intermediate deflection at any point, displacement or at any point. So let's say we have a truss, and just to recollect, in trusses what do we say? Let's say it's just in local axis, so I have u1, right, and displacement at another joint is u2. Now I'm interested in finding out the displacement at any point x distance from the first point, right? So let's say this is point 1, which is at a coordinate of x1, and this is second point, which is at a coordinate of x2. Now let's say this is at some distance x from x1. So how do I find out the displacement at any point x? Any idea? The displacement at these points are known. U1 is known, U2 is known. How do we know that? Because after doing the analysis, we will be able to solve for U1 and U2, right? We know the local coordinate matrix, right? So F1, F2 are related to, through a matrix method, we can find out U1, U2. So one of them will be given as boundary, some of them will be given as boundary condition, which would be known, and some of them may not be given, which we would solve for using the matrix methods, and we would find out the displacement at both u1 and u2. We would find it out. Now the question is, how do I find out u at x? Any idea? Any suggestion on how do we do that? What is it? It's not possible. But if we want to find out, let's say we are interested in finding it out, how do we do that? Nothing is possible in finding out structures, right? In every point we should be able to find out. Hmm. Can you please say it again? I didn't hear. So one thing that you can note is that you can see that forces F1 is given here and F2 is given here, and at last you would find out that F2 equal to minus F1 because equilibrium has to be there. But just for time being, we'll say it is F1 and F2. So the force at this point, will it be force in a truss member is always a constant, right? And because it's an axial member. So you take any truss, the force will be F and F, right? So at any point you take, it will be subjected to axial force of F, right? If you take a small portion of the beam, it will be subjected to F only, right? If this is the case, we know that axial force is going to be constant throughout the member. If axial force is constant, then we know that strain is also constant, right? Because stress and strain are, so we know that strain, I hope you know all this, U is equal to F delta B. So you can, strain is equal to stress by Young's modulus, right? And you know that stress is equal to F by A. So if stress force is going to be constant, area is constant for the whole beam. So we know that strain is going to be constant throughout the beam. If strain is constant, what will happen to displacement? How is strain and displacement related? Strain is nothing but gradient of displacement, right? So I know du by dx is what? Strain, is it not? So I can find out, I know that strain is constant, so displacement will be a linear function. So you just think, if you are not able to understand this, just think of a bar which is just subjected to an axial force F. What will happen to displacement? The displacement, if I draw the displacement profile, displacement at this point will be 0, right? And at this point it will be maximum, it will move the maximum delta. So at this point I know the displacement is going to be maximum, which is delta. How will the displacement vary between this point and this point? It will be linear, right? Because strain is constant. So since strain is constant, I know displacement will be linear. So this is a displacement profile of the stress problem, right? Is it not? So I know u is a linear function. If u is a linear function, I know it should start with, it should be of the form a plus bx. This is a linear profile that I can have, right? So u should be of the form a plus bx. If it is of the form a plus bx, then I need to just find out these two coefficients. If I find these two coefficients, I can find displacement at any point. That is all I have to do, right? So how I would do that is, how do I find these two coefficients? I know two other things from here. I know displacement at this point is u1, displacement at this point is u2, right? So what I will do is, I will say displacement at point 1, which is nothing but at x1, right, is equal to, I'll just substitute a plus b into x1, right? And what is u2? u2 is equal to a plus bx2. Now I can solve for a. I have two equations. I have two variables. What are the two variables? A and B. A and B are the variables which I don't know what they are. So I'll just mark them with red so that we are knowing that we don't know them. Now how do we solve for A and B? We have two equations, two variables. We can solve for them using substitution or elimination method, right? So I'll just subtract these two equations. What do I get? I'll get u2 minus u1 is equal to, okay, u2 minus u1 is equal to b into x2 minus x1, right? So I know b is equal to u2 minus u1 divided by x2 minus x1. What is x2 minus x1? x2 minus x1 is nothing but L, right? L is the length of the beam, right? So let's say this distance is L, okay? So I have found out B. So similarly, can someone solve for A and say, how do I solve for A? I can substitute in any one equation to get A. So let me say I'll take the first equation, so which is u1 is equal to A plus b into, I have a plus b into x1, right? B I already know, so I'll just substitute this thing here, u2 minus u1 divided by L into x1, right? So what do I get? u1 is, I mean a is, I'll get a to be u1 minus u2 minus u1 divided by L into x1, right? So I found out both a and b. So I have known these coefficients in terms of displacements at each end, u1 and u2, which I already know from matrix method of structure analysis. So once I have solved for u1 u2, I can find out a and b. Once I know a and b, I can find displacement at any point, because displacement at any point is nothing but a plus bx, right? This is what we had assumed earlier. A plus bx is the displacement at any point. So we can find out displacement at any point using a and b, which where a and b have been already found from here. right? Yeah. So interpolation. What did you say? Yes. Uh, you mean this one, right? Yes, it's actual displacement. It is just elongating. I am saying that if displacement is marked in a as a plot, uh, yeah. So the thing is, this is not the deflected shape. This is not the deflected shape. This is a graph which shows how the x displacement varies along x. This is not the bar. This line is not the bar. Okay. This line is just saying that as we move from x, how much will be the displacement u. Okay, that value I'm just plotting here. How do we plot, right? So that value will increase, and here the displacement at this point will be maximum. Okay, so it's just elongation problem. It is not vertical deflection, it's a horizontal deflection, right? That is why we can see that the displacement at this point is delta, which is same as what we are drawing here. This is just displacement of x, is not the deflected shape. It's just the plot that shows the displacement and with respect to span. Is it clear now? Okay, so this triangle has nothing to do with actual deflected this thing. It's not deflected shape of the bar. It's not how deformed shape of the bar. I mean, there's not deformed shape of the bar. It shows the variation of displacement with respect to the span. Okay, so I just wanted to say that it is linearly increasing. That is why I had drawn this graph. My intention was to show that we know that the displacement, the strain is constant. If strain is constant, then we know derivative is constant. That means that u itself should be a linear function. Okay, so that linear, we can see here that it's linearly varying. That is all we are trying to say here. And it's starting from 0 here because of the boundary condition here. For different problems, it could be different. Okay, but anyhow, we know that it is a linear variation between u1 and u2. Okay, that is why we are able to assume this linear variation. Once we have a linear variation, we know we want to solve a and b using the boundary conditions u1 and u2, which we would have solved already using matrix methods. So once we have u1 and u2, we can solve a and b, and we find that u is totally known now because a and b can be found out in terms of u1 and u2. X1 and x2 are also known. Those are the nodal coordinates, right? Right? Okay, so now I'll just simplify substitute the whole thing and make it more elegant to look like. So what I'm saying is I'll just substitute u is equal to, u is equal to a plus bx, right? What is a? A is equal to u1 minus. Don't think that it's what we are doing is not worth it. Actually, after we do all this derivation, you would be able to see a very interesting result. That is why I'm showing this, and also it lies basics to the finite element process, which you would be learning subsequently, or which you would have already heard about it. So if you can understand this, you would understand a very important concept of finite element analysis, which is what we call as interpolation function or shape function, right? So there also interpolation means what? Interpolation means we are interpolating between something, right? So we are finding out displacement between two things, interpolating, right? So that's what we are going towards it. So even though we are moving slow, I would actually say that this is needed, essential, and we have to go slowly. So u2 u1 minus u2 minus u1 divided by L times x1, this is a, right? And a times a plus bx is what we have, plus b is u2 minus u1 divided by L times x is what we have. Now in this case, we will just write it in terms of u1 and u2. Okay, so what I mean is, let's pick up u1 terms and all separately and u2 terms separately. So what do we have here? We have u1 from this u1, and then we have plus u1 by l, u1 by l into x1, right? So I'm taking only this term because that only has u1 term, plus or minus u1 by l into x. I took it from this term, right? So this is u containing u1, so I can take u1 outside of all this, which I'll do later. Maybe I can do it here itself. So what I can do is, I'll just erase u1 from everywhere and take u1 outside. Okay, plus, and similarly I can take u2 outside and take all the u2 terms common. So I have minus u2 by l here, which will give minus 1 by x1 by l, right? And then what are the u2 term I have? 1 by lx, right? So I'll have plus x by l, right? So I can simplify this and write it as, I have l plus x1 minus x. Let me know if I have made any mistake. I'm not sure if I would have made any mistake. Divided by l. Okay. What is l? L is nothing but x2 minus x1, right? So I'll just write it as x2 minus x1 so that x1 x1 gets cancelled, and I will just have this thing as x2 minus x divided by l times u1, u1, okay, this is 1, plus x minus x1 divided by l into u2. This is a very important result that we have to note here. Okay. Now what we are saying is, what we have at last done is, we are saying displacement at any point is something times u1 plus something else times u2, right? This something has x term in it, which means that it is varying with x. As we go along x, it is changing. Similarly, here also there is an x term, which means that something, it varies along the span, right? This u1 and u2 are already known to us. These are displacement at the ends, right? So we'll just call this first coefficient as some n1. Okay, it's just a name that we are giving. Okay, so this whole thing we'll call it as n1, right? This whole thing we'll call it as n1, same as this. And similarly, we'll call this thing as n2. Okay, so what we can write is, we can write u is equal to n1 times u1 plus n2 times u2. So we can find out displacement at any point if we know the displacement at the endpoints, given that these things are known. These things are what are called as either shape functions or interpolation functions. Okay, so you have these n1 and n2 being called as interpolation functions. Why function? Because they change with x, like they are function of x. Okay, so what is n1 and n2 if you see carefully? N1 and n2 is nothing but x2 minus x by l. So how do they vary with x? They're going to change with x, right? x2 is nothing but coordinate of the second point, x1 is coordinate of first point, and x is just changing as we move along x, right? So if you plot it along x, what do we see? We plot it along x, this is going to be x-axis, and this is going to be how this function is going to vary, n1. So what is happening when x is 0, I have x2 by l, right? and as x is going to vary and x is going to become, so when x is not going to be 0, this x is going to be x1. At the minimum x can be x1, right? It starts from x1 to x2. So if you remember the bar, it is having x1 here and x2 here. X is any point here, right? So x can be either x1 and it can vary till x2. So x becomes x1, then I have x2 minus x1 divided by L. What is that? That is L by L, which is 1, right? So when x becomes x1, which is the starting point, and this is the ending point x2, when x becomes x1, I know it is just 1, right? And it slowly, when x increases, this whole value decreases because negative, right? Becomes negative. So when x becomes x2, which is the extreme value in the right point, it's 0. 0 by L is 0, right? So I just go linearly from 1 to 0. So n1 is nothing but it's a function which varies from 1 to 0 linearly along the length of the bar, right? And similar calculations we can do for n2. What is n2? N2 is this value. When x becomes x1, this whole value becomes 0. So I know that this is 0. Starts at 0 at x1. And when x becomes x2, x2 minus x1 is L. So L by L is 1. So I know it increases to 1 when x becomes x2. Right? So these two are interpolation functions. Now I can say that displacement at any point is, you take this function times u1 plus this function times u2. So you can get displacement at any point. So now you have solved the entire problem, because before talking this we had only discussed about how we can find out the joint displacements. We never talked about how to find out displacement at an intermediate point. Although we can find shear forces, bending moments, everything at intermediate points using just cutting the section and taking equilibrium. But we didn't talk about how to find out displacements and rotations, right? Now only we have talked about how to find out displacement at any point using the concept of interpolation function, which is nothing but basically we have taken linear variation and then we have found out using boundary conditions we are able to solve for this, right? So any questions at this point? If there are no questions, then we can proceed on to how do we find out interpolation function for beams. So that is what is more important, because that's what we will be frequently using in our analysis, right? So we can extend the same concept to analyzing beams. So in beams, what are we doing? In beams we have a beam subjected to n forces and n moments, right? F1 and M1, F2 and M2. So first we need to know, in the while solving stresses, what did we see? First we found out how is the variation of displacement. We knew that it is going to vary linearly. Once we knew that, we were able to uh, substitute a linear function and we found out the coefficients for that. That's what we did, right? So here also we need to know how this displacement is going to vary. What is the order of, what is the degree or order, right? So it could be linear or it could be quadratic, it could be cubic, it could be fourth order and so on. How do we know what is the order of this function? How is the displacement going to vary along x? How do we know this? In stress problem, what we said that the strain is going to be constant. When strain is constant, we know displacements are going to be linear, right? In this beam case, how do we know how displacements are going to vary? We have to use Euler's deflected shape, but how do we know the order? How do we know whether it's going to be quadratic, cubic, or so on? I know that it's not going to be linear, because if it is going to be linear, it has to be straight, deflecting straight, right? So which is not going to happen. I won't have it to be something like this. Displacements linear means, so I know that it's going to have something like this and so on, right? So I know it's not going to be linear, but how do I know what the order is? So that you have to use the condition that we know, since only joint laws are being applied, we know that the moment is going to vary linearly. This is going to be m1 at this point. If I draw bending moment profile BMD, I know it's going to be m1 at this point and m2 at this point, which can be negative or positive, does not matter. So I'm just assuming it to be positive, and this is what will be the linear variation of bending moment, right? Because if the forces also will cause a linear moment variation, moments will remain constant, so therefore I have a linear variation between these 2 points. This is the BMD, bending moment diagram, right? So if I know bending moment is linear, we have already discussed this, I hope. So let's say we have bending moment is a linear function a plus bx, right? Then what will be the variation of displacement, which is y of x or u of x? Bending moment is d square y by dx square into ei, right? So I know that is equal to a plus bx. Then if I double integrate this, what do I get? I know y should be some function, let's say a dash plus b dash. So yeah, I'll double integrate this. Linear becomes quadratic, quadratic becomes cubic. So basically I'll have a cubic equation. So I can write a plus bx plus cx square plus dx cube. Okay. So I have four unknowns. Now I know that I will have four unknowns. I have to solve for four unknowns, right? So, but here again we are known with four things. What are the four things that we know? We know displacement at this point. If I draw the deflected shape, probable deflected shape for this, it will have something like this. Okay. So this is the undeflected beam, and after deflection, I would expect something to be like this. Okay. So I'm just drawing some, or it could not. It could be something like this. Okay. Okay, there will be, we know u1 and we know theta 1, we know all these things from structure analysis. u2 we would have found out already from doing matrix method, right? And we also know theta 2. So once we know all these four things, we can solve using these four quantities. We would be able to solve for these four unknowns, just like how in a truss problem, using those two known quantities u1 and u2, we were able to solve for a and b. Right, same procedure we should do here, which I'm not going to do because it's lengthy process, but the principle remains the same. Basically what we have to do is that we know y at x equal to x1 is going to be u1, right? So I'll put that equation just like what I did here, what we did here, right? So we know that u1 is going to be a plus bx1 because I'm going to substitute x equal to x1. I know displacement is u1, right? Similarly, displacement at u2 is, I will substitute x equal to x2 and I'll get u2. Now here what we have to do in extra is, in excess is that not only y at x1 is known, which is u1, y at x2 is u2. These two are not the only knowns. We also know that y dash, which is differentiation of x1, is going to be theta 1 and y dash at x2 is going to be theta 2. So we know four conditions. With these four conditions, we should be able to solve for A, B, C, D and write it in terms of U1, U2, theta 1, theta 2. Once we do this homework, then we would be actually able to see that U is some N1 times U1 plus some N2 times theta 1 plus some N3 times U2 plus some N4 times theta 2. This is what we would observe. We would be able to write like this, just like what we did for a truss problem, where N1, N2, N3, N4 vary along the displacement, vary along the span. They are a function of x. We are not just constant like u1 theta 1 u2 theta 2. They vary with displacement, with span. Okay, therefore we know how they vary. Actually there will not be a linear function. In the previous stress problem we observed that n1 and n2 are just has a linear variation of x, therefore they were varying linearly with x, their diagrams are linear. But here what we would observe is that there will be a cubic function of x. Therefore, what we would observe is that they will vary cubically with x. Okay. So if you want to draw their variation with x, how do you assume? How do you find out? You can actually guess it. N1. How does it vary? Can you guess how N1 will vary with x? What is N1 actually? N1 is going to be the displacement is equal to u itself if everything else was 0. How would everything else become 0? That means that theta 1 should become 0, u2 should become 0, theta 2 also should become 0. If all these quantities become 0 and u1 becomes 1, then n1 is same as displacement, which means that if I give a unit displacement at 1 and theta 1 becomes 0, u2 also becomes 0, theta 2 also becomes 0, then whatever is the variation displacement profile that I would expect is the n1 function itself. So therefore its variation is similar to is same as the beam deflection problem when I would give a unit displacement here. So that's it. This is how it will vary. So this is x2, this is x1. Okay, and you can do for similarly for n2. How do you think n2 will vary? N2 is same as displacement profile, the entire displacement profile. If u1 was 0 and theta 1 was 1, right? So we know we have done similar problem for solving the stiffness matrix, right? While solving the stiffness matrix also we did something similar, right? So it will be variation like this, and similarly you can solve for n3 and n4. Okay, so this is how you know the variation of x1, x2, x3, n1, n2, n3 and n4, which if you want to actually find out the equation of these things you have to do the whole homework that we skipped here, but the procedure is known to us, so that's why we skipped it here, right? This is how you find the shape function, interpolation functions. You can using this interpolation function you can find out displacement at any point now, if you know the displacements and rotation at the ends, right? Okay, are there any questions in this? By the way, I would like to emphasize here that this, even though it looks very similar to what we had done in what we had done use while finding out the stiffness matrix itself, we were doing something similar, right? You giving unit displacements and finding out the total uh, uh, thing. But the difference here is that while giving unit displacement at one n and making all other displacements to be 0, what we were doing there is to find out the n forces and n moments, not the deflected shape. What we are doing here, the shape functions are not with respect to forces. It is only a kinematic problem. Here we are only interested in giving a unit displacement at one point and making all other degrees of freedom to be 0 would give us a deformed shape. That deformed shape is what is the shape function. Okay, that's the difference between what we had done while finding out the stiffness matrix and what we are doing here. Although there also while finding all the 4 columns we had done a very similar exercise of making degree of freedom of one thing to be 1 and everything else to be 0. There we are only finding out statics, we are only finding out what are the n forces generated due to that displacement. Here we are finding out what is the deformation that it is formed due to a unit displacement. This problem we can solve it using double integration method or something like that. We can solve it directly using double integration method to solve these problems, or we have to adopt this procedure that we have discussed here. Any one thing works out. Okay, since you know the concept of shape function, you can solve these four problems of giving unit displacement and finding out all the other displacement, making all the other displacements to be zero, and finding out what is the exact y of x. That y of x will be nothing but n1. Right, similarly find out y of x in this case, this beam, that will be n2 and so on. Okay, so anyway you can work out to find out the shape function or interpolation function, right? Okay, I hope this gave a bit of idea on how to find out the intermediate displacements, right? Fine. And then moving on, so this completes the whole details on beams, analyzing beams using stiffness methods. So if we have to talk about frames are not going to be significantly different from what we had discussed in beams. It's just an addition of both the problems of trusses and beams. So in trusses we had only axial forces. Beams we are having shear forces and bending moments. So in a frame problem, we will be having both axial forces as well as shear forces and bending moments, right? So mixture of all these two things put together is what is a frame structure, right? So we can actually, I'm not going to discuss all the details because I hope you would have seen the lecture as well as its direct extension of what we have seen already. So you can have 3 degrees of freedom at each node instead of just 2. Earlier we had seen only the perpendicular shear force and the moment. Now we can have axial force as well. So in the global coordinate you will have a transformation matrix, right? So this is how you change it. For the moments you don't need any transformation because even if you rotate it anywhere in 2D, the moment is going to be the same. But these two forces that are going to be applied in a global coordinate would change depending upon, would contribute differently towards being axial force or shear force depending upon the direction, right? So you'd have a transformation matrix just like what we had in trusses, and then you can, from local coordinate you can transfer to global coordinate, and then you can use that global coordinate stiffness matrix for different elements, different frame elements, and then you can assemble them to get the stiffness matrix for the entire structure. So that process is very routine and we have already seen it multiple times in the course, so I'm not going to give all the details here. So with this, I also hope it completes on the discussion on frames as well, right? So if you have any particular questions on frames, then we can discuss it here now. That's fine. Yes. Yes, you are absolutely right. This is not actually, this is not a what determinant? What determinant? There are two determinants. Right. Yes, you are right. You are right. So you are. So this is actually not a very simple question that you are asked. It's a very detailed, very fundamental question which only comes if you have understood things very deeply, right? So I appreciate for it, you for asking this question and bringing this up so that it is also going on record so that many people would be able to understand this. So you are right in saying that we can analyze, use matrix methods or in general displacement methods to solve a statically determinate as well as a statically indeterminate problem, right? Now we are also right in saying that we don't use displacement methods to solve a fixed beam. The idea is So the basic, I would say that how this displacement method developed, if you go back and see how we came across, how did we develop this displacement method, you would see that actually it came only after force methods. Okay, only after having studied force methods we can even actually understand displacement methods, because a part of displacement methods is it's built on a step with assumption that force methods are already known to us. Okay, if we don't know force methods we cannot proceed on to displacement methods. Okay, so now what we are just saying is that if you have a highly statically indeterminate problem, okay, then you can just say that it is so much statically indeterminate that it is fixed at all points. Okay, what is the maximum statical indeterminacy you can have in a structure is to fix it at every point, right? That will create so many redundants, is it not? That will give so many unknowns to the structure and then it will make it statically indeterminate. You can say that from statically determinate point you are reaching a maximum of statically indeterminate point by making everything fixed. Okay, now if your structure is somewhere here, okay, this point is statically determinate. Okay, and this is fixed. This is the most statically indeterminate problem you can have. Okay, anything else is just statically indeterminate. Now let's say your structure is somewhere here with so many redundants and so many uh, unknowns, right? Unknown forces, right? Then we can say that instead of say finding out too many unknowns, these all will increase too many redundants, right? Instead of going this way, which will give us too many redundant unknowns, we can solve it like this. We can start from here and solve it from starting it as fixed beam, we are solving it. Okay, that is what we are coming. This is all about displacement methods. We are saying that we will solve it assuming that we know everything about fixed beam, and then we'll come like this. Okay, now if your structure is just slightly statically indeterminate, if you are in this point, then it is not wise to go this way. It's not wise to use displacement methods. For example, if I have a statical indeterminacy of 1, then I would not be very it is not very tempting to use a displacement method. I would just go by a uh, force method itself. Okay, so when do we choose force methods and when do we choose displacement methods itself depends upon what is the static indeterminacy or kinematic indeterminacy. We'll compare them and then see, right? Now when we has, let's say that we have decided to go on with a displacement method. once we have uh, Once we have finalized that, then we assume that we know how a fixed beam behaves. We assume that. Okay, that means that's a starting point, and then we reduce on and we can find out what is the extra kinematic variables that are there, and then we solve for it using displacement method, right? Once this is the assumption, that means that the assumption cannot be solved, right? So for example, in Euler-Bernoulli theorem we say that plane sections remain plane, right? When we are starting with that assumption, is it possible to use Euler-Bernoulli principle to prove that plane sections remain plane? Or can we show that plane sections remain plane using Euler-Bernoulli's principle? No, we cannot, because that's where we start. That's the first step we take in starting that theory. Then we cannot prove that assumption. Assumption is something that we start with, right? So similarly in displacement methods we say that fixed problems are somehow solved. I don't know how to be solved, but we assume that it is solved. And then we say that if there are extra unknowns from the fixed kinematic unknowns, okay, extra kinematic unknowns from a fixed beam, some suppose are getting released, then we will only solve for them. Okay, that is how we are solving it. Therefore, now how do we know that? How do we solve for fixed beam is a separate question. That we are able to solve just because we know other methods which are force methods. That's how we are able to solve for it. Okay. Now if you want to solve a fixed beam using displacement method, it doesn't make sense because that's the starting assumption point. That's what we say is a kinematically determinate beam, because we say that it's known to us. That's where we start, and then we say how many extra kinematic unknowns we don't know in an actual structure. Okay, so maybe you might have to think a bit more on this, but I tried to give a broad sense of what it is. So did it partly answer your question on? So then, when we say that matrix methods can be used to solve both statically determinate as well as statically indeterminate problems, we should actually add a clause saying that except kinematically determinate problem. Actually, it's not that we cannot solve it. It's just that, yes, I think, yeah, we cannot. If we, yeah, no, actually, yeah, kinematically, yes, I understand. Yeah, you're right. Yeah, you're right. So fixed beam, when we have an intermediate load, we solve it using, we have fixed end moments which we should know from force methods. Okay. Yeah. Yeah, thank you. But actually, there is a way to solve it. You can actually split it into different elements, and then if you give it to a computer, it will anyway solve it, because what it will do is it will take the fixed beam. If you are saying that you want to know the fixed end moments for this, for a load subjected to like this, then you don't need to treat it as one node at element, right? If you only treat it as one single beam and then want to solve it, then it might not be directly possible. So what you can do is that you can split into two nodes, right? So that if you make this problem, then actually this is also not a fixed beam, this is also not a fixed beam, then you would be able to solve it anyway, right? So that's how, if you put it in a program, then it would be able to solve it in as a two element problem. If you give it two nodes, I mean two element problem, then it would be able to solve it. Okay, so yeah. Okay, then if are there any more questions? Yeah, I hope they will be uploading it soon, because tomorrow seventh week is starting, right? Yeah, they will be uploading it soon, probably by today, I hope. Okay, yeah. Then we can stop it here if you don't have any more questions. Thank you for attending.